This problem, imagine a situation where we got some light traveling in water. Hits the surface of the water. And we're right at the critical angle where the angle of incidence is such that if it was any smaller, we'd get refraction. Light would actually pass through the surface. But if it was any bigger, we'd get total internal reflection. We're right at the threshold where you don't even know what to call it. The light comes off at a 90-degree angle with respect to the normal. That's the critical angle. We're talking about light that's traveling in water, where for water, the index of refraction is 1.33. And on the other side of the interface, we've got air with an index of refraction of 1.00. According to Snell's law, N1 sine of theta 1 is equal to N2 sine of theta 2. At the critical angle, the theta 2 in question is 90 degrees. So we've got sine of theta 2 is N1 over N2 times the sine of theta 1. Now here's the way I'm going to look at this. To solve for theta 2, the angle of refraction, I would have to take the arc sine of this side. Now, if this is less than 1, I've got no problem taking the arc sine of it, and in fact, I do have some refraction. Light gets through. If it's greater than 1, I can't take the arc sine of it, because there is no angle whose sine is greater than 1. So you can't take the arc sine of it to find the angle whose sine is equal to it if it's greater than 1, which would correspond to a case of total internal reflection. The light would remain internal to the water. And the boundary case, or the threshold case, is when it's equal to 1. If it's equal to 1, then theta 2, the arc sine of 1 is 90 degrees, and the theta 1 that makes it so that this is exactly equal to 1 is the critical angle. As theta 1, the angle of incidence for refraction is equal to the critical angle that it has to be equal to make this one. So N1 over N2 times the sine of that critical angle, sine of theta 1 when it's at the critical angle is 1. We can solve that for theta c. I'll multiply both sides by N2 over N1. And theta c is the arc sine of N2 over N1. N2 I know is the air side because that's the material on the other side of the interface from the side in which the light is initially traveling. So it starts out in one medium and then goes into another medium after it passes through the interface, or if it were to pass through the interface, it would go into another medium. That medium that it would go into is referred to as the second medium, whereas the medium in which it's initially traveling is the first medium. So in our case, the second medium is the air, as I have indicated up there, and it's got an index of refraction of 1.0. So we're taking the arc sine of N2 1.0 divided by N1. The light was initially traveling in the water. So the index of refraction of material number 1 is the index of refraction of the water, which I've looked up. It's 1.33. And if you go ahead and take the arc sine of that, you get 48.753 degrees, which rounds to 3 sig figs to 48.8 degrees. You might think this is that ambiguous case where I gotta round this number. It's either do I keep it the same or do I bump it up by 1? Well, there's a 5 next, so you might think that's the ambiguous case, but no, there's something after that. As long as there's some non-zero value in any digit after that, you got to go up after the 5. So I take it up to 48.8 degrees. That 7 becomes an 8. And thus, the critical angle for water, that is, for light traveling in water and encountering a water-to-air interface, is 48.8 degrees. And that answers the question asked in SAC 226, problem number 3.